let's get started up in this comparison test. So, suppose we have AN and BN, which are positive, and it's the notation of the book. AN is less than or equal to BN for all n. Then the following is true. If the series, so n equals 1 to infinity, Bn converges, this implies the sum n equals 1 to infinity AN converges. And conversely, if the sum 1 equals infinity AN diverges, this implies that the sum n equals 1 to infinity Bn diverges. And this is incredibly natural, right? So let's draw the picture representing this information. So this collection is the blocks that represent Bn. So I've drawn them to be decreasing just for convenience. They don't necessarily have to. Okay. Yeah, so these are the Bn. So this is height B1, and this is height B2, and so on. If I speak too quietly, if I forget that I don't have headphone microphones, just interrupt and tell me to speak up. And these guys here are the AN. So let's draw on this picture this information right here, right? So as always, this is a language we use to describe pictures. So we're gonna put the pictures right here that are the meaning of the expressions we've just written on the board. So this is our collection AN. So this is A1, this is A2, and so on and so on. This one could be this one could be this one. Yeah? The meaning of this inequality is exactly that these blocks are underneath the blocks that give the Bn. Yeah? So if we have that AN converges, that exactly means that the area of all of these blocks, when we put them from this very first one all the way to the very last one, well, not the very last one, but all the way to infinity, yeah, the area of all of these blocks is finite. That's what convergence means when we have a collection of positive terms. Yeah? And I said AN? Sorry, let me do that the other way around. Yes. If all of these guys, Bn converges, that means the area of all these green blocks converges. Yeah? And since the area of all of the red blocks is obviously less than x, the area of each individual red blocks is less than the area of the block it's contained inside, that means the area of all these guys converge. The area has got to be finite, just from the picture. Yeah? Give me either the icon or the thumbs up if you're with me. Or give me the thumbs down if that's not clear. And type in here in the chat. We don't seem to have many people. This is an obviously true fact. If Bn converges, the area of all these green blocks is finite, then the area of the AN is finite. And the converse is also true. If we have the area of all the red blocks is not finite, so we sum together all these blocks and it has infinite area, then for sure these guys have infinite area too, because again, they are above, so the area of all these Bn is bigger than the area of all the AN. Yeah? So this is a very natural, very simple principle, and we've used it. We've implicitly used it because it just makes sense. I haven't stated it as a theorem, but it's just immediately true, and we can use that to figure out some series pretty quickly. So, for example, this series. Determine if the sum n equals 1 to infinity 5 over 2 n to the 3 plus 4n plus 3 converges. Solution. Well, if we look at this guy right here, yeah, then since we are putting extra stuff on the bottom, we notice that this expression is less than 5 over 2n to the 3, which is just 5 over 3 times 1 over n to the 3. Yeah, and for sure this converges. And the sum n equals 1 to infinity, 5 over 3, 1 over n to the 3 definitely converges. We can just pull it out, this thing. And we know this converges because we've learned that whenever we have the sum of 1 over n to the p, for some p where p is bigger than 1, then it converges. That was one of the consequences of the integral test. So converges. So original series, so let's just call it star converges. Easy, right? Okay, let's consider the next example. What about this? What if we have the sum n equals 1 to infinity, 1 over 2 to the n minus 1. Okay, tell me about this guy. Okay, but let's check it out. So if we have 1 over 2n minus 1, the natural thing is to compare it to 1 over 2 to the n, yeah? Yeah? But let's compare these two guys. If we look at the denominators, which is bigger, this one or this one? The second one, right? 2 to the n is bigger than 2 to the n minus 1, yeah? Which means that this expression here is smaller than this expression, so the inequality goes this way around. Yeah, so this guy is underneath. This is the an, yeah? This is the red blocks underneath. Yeah? So we know that this thing converges. Does it help us to conclude that this guy converges? Not at all, yeah? It doesn't help at all. So if we have that our red blocks in this picture converge and we have the green blocks above it, that doesn't help us say anything about the green blocks. It might converge, it might not. They're above it, right? So it could be that the area of all the green blocks is infinite, or it could be finite. We don't know. The fact that we have something underneath it that is finite is not helpful. Doesn't yield any information. Doesn't force the green blocks to do anything one way or the other. But I get what you're saying. This is indeed something that seems to be going down to 0 incredibly fast, right? 1 over 2 to the n minus 1 for very large n. This 2 to the n minus 1 is really a lot like just 2 to the n. Yeah? So 1 over 2 to the n minus 1 is going down to 0 a lot like 1 over 2 to the n. So we'd expect it to converge. But we can't directly apply this inequality. This doesn't help us. Yeah? Yeah? So what we need is a different tool. We need a different tool to allow us to conclude this. And it turns out there is a different tool. There is a principle, a theorem, that allows us to say that since this guy is really incredibly a lot like 1 over 2 to the n, the fact that 1 over 2 to the n does converge means that this converges. And that thing is called the limit comparison test. And it's a more sophisticated version of this principle. Yeah? And that's what I'm about to teach you. So this is the motivating example. This is why we need this stronger thing, this limit comparison test. Okay, so let's state it here, and then we'll use it. Well, then I'll draw pictures, and then we'll use it. So, limit comparison test. If we have that an and bn are positive terms, and the limit as n goes to infinity of bn over an equals L, where L is not equal to 0, this series, the sum n equals 1 to infinity an converges if and only if the sum n equals 1 to infinity bn converges. Which means that if we know either one converges, it implies the other one converges. If we know either one diverges, it implies the other one diverges. In other words, whatever an does, bn has to do. And whatever bn does, an has to do. They are completely linked in terms of convergence or divergence. They're the same thing. Huh? Yeah? Okay, so I'm going to raise the board. You people, in the meantime, try and draw a picture that represents this information. Okay? And then from that picture, try and give me an explanation of why you believe this. Yeah? So draw a picture that represents this information, and then try and explain why you believe this principle. Yeah? Cool. And a hint of how to do this is to consider this sequence. So maybe draw the series as blocks, and then draw what the sequence bn over an looks like. Yeah? Okay. Okay, let's put down the hypothesis, the information that we have. So we have that the limit as n goes to infinity of bn over an, it exists at some number L, and it's not equal to 0. Okay? And then what we want to conclude is that whenever an converges, bn converges, and vice versa. Then the sum n equals 1 to infinity, an converges. If and only if the sum n equals 1 to infinity, bn converges. And logically, that's equivalent to saying that the sum 1 equals to infinity an diverges if and only if the sum n equals 1 to infinity bn diverges. Okay? All right, let's try and draw the information. Okay? We're going to make our life simpler. We're going to consider a special case that has all the important information. It just makes our pictures easier. So assume, for simplicity, that L is equal to 1. Yeah? So let's start drawing our information. So this is Bn and if I'm going to draw the An, what's it going to look like? Well, we know that the ratio of Bn over An tends more and more to 1, right? So whatever these blocks start off as, so sometimes they could be above, sometimes they can be below, sometimes they can be way off. But increasingly, as we go along, the ratio of An over Bn is closer and closer to 1, right? Yeah, which, saying another way, that's like saying that An is more and more between, say, 101 and 99% of Bn. Yeah? In fact, you keep going, it's more and more between 100 and 0.1 and 99.9 of Bn. Yeah? That's exactly what this is saying in the case when L equals 1. Yeah? You see what I mean? So actually, let me write down this hypothesis down here. So the limit as n goes to infinity of Bn over An equals 1. Yeah? So both of these numbers, sequences of numbers, might be tending to 0, but their ratio tends more and more to 1. Yeah? So if I'm drawing this, then what I'm going to draw is that these guys that represent the An, they look more and more like the guys that represent the Bn, right? If this ratio is tending towards 1, then as I keep drawing it to the right, then it's harder and harder to show there's any difference between the two. Because again, you can think of this as well, this is exactly like saying that no matter how small a percentage difference you want, say the range between 100% or 100.00000 something and 99% 0.9999999, you can find n sufficiently large so that for all n bigger than that number, then the percentage difference between these two guys, an and bn, is less than that. You see what I mean? Yeah, that's exactly what this thing means, that the ratio of these two guys tends to 1. Yeah? Yeah? Because, what does this mean? So long as we go far enough to the right, let's draw the sequence an over bn. So look at, I should say bn over an. What is the sequence? Well, this is more and more close to 1. So let's put 1 here. We know what a limit means. A limit means that if we put any tiny strip around 1, then ultimately, if we go far enough to the right, all the elements of our sequence bn over an lie within this strip. That's exactly what a limit means. We've learned that. Yeah? So what that means for all large enough n, we have that 0.9999, however many nines you want, 0.9999, is less than bn over an, which is less than 1.0001, right? For example. That's exactly what this says when the limit is 1, right? That's what we know. And it doesn't have to be 0.9999. It can be 0.9999999, or here it can be 1.000001. We can make this as close as we like to being 100%, just a little bit underneath it, and 100% just a little bit above it. No? So it really is the case that when we draw the picture, it's harder and harder to distinguish between these blocks. Are you all with me here? So let me complete this, or any precision we want. All right, so if this is our picture, if this is what we see, right, then it seems very natural to us that whatever is happening with respect to an will also be the case for bn. Yeah? Because we can hardly tell the difference between these two series as we let n get bigger and bigger, right? Yeah? Yeah? In particular, as a consequence of this, we don't even need this level of precision. We know, so let's call this thing star. So we know that, oops, for all large enough, emphasize all large enough n, we have that bn over an is less than 2, say. For sure that's true. Since this is true, huh? So bn is less than 2 times an, yeah? For all n bigger than some particular number, let's call it capital N, yeah? So therefore, if this is true, then if an converges, then 2 times an converges, and therefore bn has to converge just by the ordinary comparison test, yeah? So if this is true, then if we sum from capital N onwards, then the fact that this guy converges means that this guy converges. And the first terms from 1, 2, 3 up to capital N, they're just finite numbers. So that's not going to affect the convergence or otherwise of this series. Yeah? So this thing is strong enough for us to conclude that if an converges, then bn has to converge. Cool. And for all large enough n, we also have, just as a consequence of this thing, an over 2 is less than bn, like this. So since we have this, then this number for sure is bigger than a half, right? So if we multiply both sides by an, then we have this inequality is also true. Are you with me? So if Bn converges, this implies An converges. Because from this, we know that the sum of An over 2 converge, because they are contained within the Bn blocks. Yeah? And if An over 2 converge, then, yeah, this is correct. If An over 2 converges, then An itself definitely converge. So that thing is strong enough for us to conclude this thing and this thing. Yeah? I mean, we can put these things together. Well, it's almost the same. We have that An over 2 is less than, Bn is less than 2 An, which is much weaker than this thing, but that's all we need. And if we have this, then this side means that if An converges, Bn converges, and this side means if Bn converges, An converges. Yeah? So if we have something like this, for all n bigger than some big number n, this thing is strong enough to completely link the behaviors of the convergences of our two guys, An and Bn. Yeah? This thing is strong enough for these two guys, An and Bn, to be completely linked in this behavior. There's no way one could do one thing and the other one can do the opposite thing. Yeah? If we're going to draw this as pictures, it would mean that if we let the green blocks be the Bn and the red blocks be the An, what would we see? We would see that if we take 2 times the An, it's contained, the Bn are contained in 2 times the An, so these things I'm drawing now are 2 times the An, right? This is 2 times An. Yeah. And if we consider a half of An, which is what I'm drawing now, these are contained in the Bn. This is the picture that represents this thing right here. So this here is half of An. Yeah, and this is true from capital N onwards. So this guy here is N, and this is N plus 1, and so on, and so on, and so on. So if that is our situation, then for sure we believe that the convergence of An implies the convergence of Bn and vice versa. Yeah? So this is a slightly longer explanation than most of the explanations I'm giving, but this is again a completely pictorial thing. This is something that is completely represented by these pictures. Yeah? I didn't have to use any symbolic stuff here at all. I could have just drawn you pictures to explain why this has to be true. Yeah? And indeed, all this symbolic stuff is just a language that describes these pictures. Not just, but this symbolic stuff is a language that describes these pictures. It's just a shortcut. Rather than drawing pictures all the time, we have this language that does it. And when we get familiar with maths, then reading this language produces these pictures in our heads, and that's why we know these things are true. Okay? That's what should be happening to you as this process evolves. The more you learn this stuff, the more it's sinking in, the more you can look at this stuff and you'll see pictures like this turning into your head, coming into your head. And that's absolutely my dream for you. I want you to become fluent in this language in the sense of being able to read this stuff, see pictures, and conversely draw the pictures that your brain, your logic, your imagination give you, and then convert that into symbols when you express your ideas. Convert that into this language. Okay, cool. So we believe this theorem now. Yeah, we believe this theorem. If this explanation isn't clear to you, please just watch it again. Look at this, give yourself this, convince yourself that from this, the convergence of An is equivalent to the convergence of Bn. And then once you believe that this means these convergences are equivalent, then convince yourself that from this hypothesis here, we have that this follows, which again is just this argument here. And all this is a special case of this thing when we've taken L to be not equal to 0. Okay, so instead of dealing with L, instead of dealing with 1, I could have dealt with L, and then I would have written L over 2 and 2L instead of a half and 2, and it's exactly the same. I just wanted to minimize things, complexity of things. All right, so this is a very important theorem because now we can answer this question that we got stuck on, which is about this series. So recall we considered the series 2 to the, we considered the series whose terms is given by this thing. Yeah? And we wanted to say that this thing is underneath the series 1 over 2 to the n, but that's actually not true because we have this. Yeah? So we can't directly apply the comparison test, but we can apply the limit comparison test because we can let the an be one of these guys and the bn be the other. So let's let bn be this guy, and let's let an be this guy. Yeah? Then if we consider the ratio of the two, then as you can imagine, as we talked about right at the beginning, these things seem to be tending to 0 in a very, very similar way, right? And we can say that precisely in the language of maths, which is exactly saying that this ratio of these terms tend to some limit. In this case, the limit will be 1. So look at this. bn over an is 2 to the n over 2 to the n minus 1. Let's factor 2 to the n from the bottom. So we have 2 to the n over 2 to the n, 1 minus 1 over 2 to the n. 2 to the n's cancel, and then that's just equal to 1 over 1 minus 1 over 2 to the n. And then as n tends towards infinity, this limit has to be 1 because this number here is getting closer and closer to 0. Yeah? Do you see what I mean? Give me the thumbs up or the icon. Perhaps it's hard to see all the way down here. Okay, cool. So, put it over here. Limit as n goes to infinity, bn over an equals 1. Therefore, whatever an does, bn does, and vice versa. And we know an converges. Huh? We know an converges, therefore bn has to converge by this theorem. Huh? So, as the sum an converges, therefore the sum bn converges. Okay, cool. So this is useful. In fact, this is more useful than the comparison test because we don't have to carefully have one guy as on top of the other. We just have to find that the ratio of the terms of the series tend to some number. That's all we need. That's all we need. Some non-zero number. Yeah? Cool. Now to make this a little bit more vivid for you people, I'm going to say the following thing. I'm going to say the following thing, that given the sum n1 to infinity, or this series and this series, if the limit as n goes to infinity, bn over an exists and is not equal to 0, then we're going to say that an and bn are married. Now this is just my notation, so you're not going to find this in Stewart's book or anywhere else, but I like to say it this way because it kind of encapsulates what's happening here. We say, we've married this series 1 to infinity an and this guy they are married, because once they are married, once we've married them by checking this, then they'll either converge together or diverge together. Once you are married to another series, you either diverge together or converge together. Yeah? Yeah? Cool. And the reason I like this language is because the way this game works is that we're going to be given some ugly series like this. This guy is not particularly ugly, but we're going to see some really ugly series. Series where it's hard to see what it's actually doing, it's hard to understand its behavior. Yeah? And what we're going to use this tool for is to extract out the essence of the series, the main important thing about the series, the main important thing about the way these terms go down to zero. And that thing that we extract out will be a very simple, clean series, a beautiful series. And then we'll show that our beautiful series that we've extracted out is married to the ugly series. And once we marry the ugly series to the beautiful series, then we are in good position because we understand what the beautiful series does, because it's simple, it's clean, we can see what it's doing. We know for sure what this series is doing. It's simple to understand. It's just a geometric series. So the way we use this tool, it's like the series marriage game. You find an ugly series, or you're given an ugly series, and your job as the series matchmaker is to find a beautiful series to marry the ugly series to. Yeah? Once you find a beautiful series, you prove that they are married by showing this limit is non-zero. Yeah? Once you've done that, then you're in good shape, because the beautiful series is easy to understand. You can just use it to conclude either things converge or diverge. Yeah? Cool. So think of this in these terms. We are given something ugly. We think we understand it. We think we know what this is like. We think we understand that this thing is basically like 1 over 2 to the n. Yeah. And then we check that. We check that this limit exists. It does exist. Yeah. Therefore, they are married. And therefore, they diverge together or they converge together. We know that the beautiful series converges, therefore the ugly series converges. Yeah. All right, we'll do some examples of this. Now we have this tool. This is very convenient. This is very powerful. Because this is a kind of formalization of what our intuition says. So just as when we started talking about this, and I asked you about the series 1 over 2 to the n minus 1, you thought it converged because it seemed to be going to 0 really fast, but we couldn't really conclude that. We couldn't fully justify that because we couldn't bound it above by 1 over 2 to the n. But the intuition is correct. The essence of that series is that basically it's like 1 over 2 to the n. And all this thing, the limit comparison test is just a formalization of that. It's just a clarification, just logically thinking about what we mean by the essence of the series is 1 over 2 to the n, or whatever beautiful series you want to marry the ugly series to. We think about what we mean by that, what's important. All right, example 4. Look at this. Suppose we have this, the sum from n equals 1 to infinity, 2 n to the 3. Let me write that better. 2n to the 3 plus 3n over square root of 5 plus n. All right, 5 plus n to the power 5. This, I hope you agree, is an ugly series. This is an ugly series. This is a complicated, ugly expression, right? So this is our ugly series, and our job is to find a beautiful series that we can marry this ugly series to, right? So look at this a little bit. Try and come up with a beautiful series that you can marry this ugly series to. Suggestions. What beautiful series can we marry this ugly series to? What's the essence of this thing? What's the important stuff of this thing? what are the unimportant parts of this series? Look at these terms. Think about how this series either goes to zero or doesn't go to zero. Think about the growth or decay of this series. That's the thing we really care about. As n goes to infinity, obviously. Okay. So what is the essence of the way this thing either grows or decreases? A lot like 2 times n to the 3 over n to the 5 over 2. Because for very large n, then n to the 3 is way bigger than n itself. So this is the dominant term on the top, right? And again, for very large n, then this 5 is incredibly insignificant. So we can forget about it. No? So just by looking at the main things on the top and the bottom, we have something like this. Yeah? And if we look at this, then what's this? Then this is just 2 to the square root of n. Yeah? Which is a very simple, beautiful thing to consider, right? Because we understand the series, the sum of the square root of n, right? What happens to that thing? Come on, what happens if we sum the square root of n? It's going to be divergent. These terms are actually blowing up. So of course, if we keep adding them together, they're going to be infinity, right? We're taking a sequence of steps where not only are they not going to zero fast enough, they're actually going off to infinity. So this thing diverges like crazy, yeah? Yeah? And the sum n equals 1 to infinity, square root of n, obviously diverges. Yeah? So if we can marry this ugly guy to this beautiful guy, then our job is done. Yeah? Yeah? So let's check. So try to marry the series. So try to marry star to the series the sum n equals 1 to infinity to square root of n. Okay, let's check. So we take this guy and we divide by this guy, or we could do the other way around because that's going to also either that limit will exist or it won't. So either way around you want to do it will be fine, right? What I mean is that if we have the limit as n goes to infinity, bn over an, if this thing exists, then as you know, by quotient rules for limits, that is the same as saying the limit as n goes to infinity, an over bn is equal to 1 over L. This you've learned. Yeah? So this thing, we can do it either way around. Let's divide this thing by the beautiful series. So let's do 2 to the n plus 3 to the n, and then 5. N to the 5, let's take this guy and divide it by 2 square root of n, like this. Yeah? So let's look at this. Let's factor out an n to the 5 from the denominator of the top term. So then we're going to have 2 n to the 3 plus n. And let's factor out the n to the 5 and then pull it out from the square root. So we're going to have n to the 5 over 2. And then we're going to have 5 over n to the 5 plus 1. Okay, and then all of this stuff is divided by 2 square root of n. Then we're going to have this cancellation of the top through this thing. So we're going to have 2 square root of n plus n to the I think it's minus 3 over 2. And then we're going to have this thing, 5 over n to the 5 plus 1, and all of that stuff is divided by 2 square root of n. And then we see good stuff is happening because then this stuff just cancels through. So then we're just going to have 1 plus 1 over 2 n to the minus 2 over this thing like this, 5 over n to the 5 plus 1. 1, and I don't need brackets anymore. And then we see what's happening to this thing, because as n goes to infinity, this thing is going down to 0, this thing is going down to 0, so the limit of this thing is just going to be 1, right? So this guy here is going to 0, and this guy here is going to 0, as n goes to infinity. Are you with me, people? Okay, cool. So let's call this thing star. So limit as n goes to infinity of star is equal to 1, which is a non-zero number. So they are married. So angels sing, birds fly, I don't know. The spring sunshine comes up, they are married. We married the ugly guy to the beautiful guy. Yeah? So, since the sum n equals 1 to infinity, 2 square root of n diverges, so does let's call this guy star star. Star star. And that's it. And that's it. So this ugly, complicated looking thing becomes a very simple thing once we find the beautiful guy to marry to the ugly guy. Everybody happy? Okay, so this is what this game is about. We see some ugly series, we try and extract out its essence. We try and find the nice, beautiful series to marry this guy to. That's what we have to do. And if we can do that, then life is very simple. And the way to do that is usually pretty straightforward. We just consider what's the important thing on the top and the important thing on the bottom and give it a go. And if you choose the wrong thing, then you won't be able to conclude the limit exists and is some non-zero number. And if you choose the right thing, then it's just some algebra and you will easily be able to conclude. Yeah? So it's not technically difficult. It doesn't involve much calculations. It involves making the good choice of the beautiful series. Let's do another example, and probably then that'll be enough on this stuff. Question 12 from the end of the section. Look at this. The sum k equals 1 to infinity of 2k minus 1, k squared minus 1 over k plus 1, k to the power 4 squared, like this. All right. Look at this guy. I'm sure it's an ugly guy. Let's try and extract out a beautiful guy to marry the ugly guy to. What do you see? What's your suggestions for the beautiful guy? All right, let's look at this guy. Okay, for very large k, then this minus 1 is not important, this minus 1 is not important, this plus 1 is not important, this plus 1 is not important. Yeah? These are tiny, tiny things when we have very large k. So I claim that a good guess for the beautiful guy to marry the ugly guy to is just what happens when we drop everything that isn't in terms of k, drop everything which isn't in terms of the highest order power of k. So this is what you could do. You could multiply this stuff out if you wanted to. You could multiply this stuff out if you wanted to. If you multiply this out, then you'd have a cubic expression. You'd have a power 3 of k, a power 2, and so on and so on. But the power 3 is the most important term because it's the growing the fastest term, yeah? And we multiply this thing out, we'd have a power 5 as the highest order term. Do you see what I mean? Yeah? Because we'll have the power 4 here, it's k squared squared, and then multiply by k again. So the highest order power will be power 5. Okay, so if we just extract off the highest order power on the top, what we'd have would be 2k times k squared, so it would be 2k to the 3. And if we extract off the highest order term on the bottom, we're going to have k, and this will be k to the 4, right? So this will be k to the 5 on the bottom, right? And that's easy. That's an easy expression, right? Because that's just 2 over k squared. That's a beautiful guy. Yeah, that's a beautiful guy. So our guess is that we can marry this beautiful guy to this ugly guy. That's our guess. Let's give it a go. So, try to marry. Okay, so we divide this thing. That is the limit, as k tends to infinity, of 2 minus 1 over k, 1 minus 1 over k squared. And then here we have k squared, and we have 1 plus 1 over k, 1 plus 4 over k squared. No? Over 1 over k squared. No? And then we can just cancel out the 1 over k squareds from top and bottom. Yeah? Because this thing is the same, I can just write this like this. I can write this like 1 over k squared times everything like this. That's the same thing. Yeah? So then I cancel the 1 over k squared from top and bottom, and then what do I have? I have the limit as k tends to infinity of 2 minus 1 over k, 1 minus 1 over k squared, and then I have 1 plus 1 over k, and 1 plus 4 over k squared. Then I take the limit, right? And then the limit of all of these individual terms I know. So the limit of this guy as k tends towards infinity is just going to be 2, because this thing here goes to 0. Yeah? The limit of this thing will just be 1, because this goes down to 0. This will be 1, because this goes to 0, and this will be 1. Yeah? So this thing is just got limit 2. It just got limit 2. So they're married. So they are married. They are married. And what do we conclude from this? What do we conclude? Why did we do this? What we conclude?
Yeah, it's converge.
It's going to converge because our beautiful guy converges, therefore the ugly guy converges, and we are done. Yeah? This is, I claim, an easy calculation because you know it's got to work out. If you do the algebra correctly, you know it's got to work out because you know that really the behavior of this thing is like the behavior of this thing. So you have a really good guess that this is going to work out. Hmm? So this rule of thumb of whenever you have a polynomial type expression here, underneath another polynomial type expression, you just take off the leading order terms, that's going to work. It's always going to work. So when you have something like this, if this is the ugly guy you're trying to marry, you can find the beautiful guy really easily just by forgetting everything except the leading order terms on the top and bottom, and that will be your beautiful guy, and that will work. That will work. Yeah? And you check it's going to work, you do the steps, you do the algebra, and you'll get to the answer. It's not like integrals where you do a slight sign change, you get a completely different expression, and you go off on a tangent. This is a robust procedure. This is unlikely to completely give you the wrong answer, even if you make small mistakes like I just did here. Yeah? Cool. All right. I want to do another one because I don't think I did this justice yet. So again, I'm overrunning. Please leave whenever you want to. I don't care if I just do this to the video and just upload it. Stay if you want to. From the end of the section. Another reason I like this is that it is quick. If you do multiple choice and you get good at this stuff, you don't have to all the details to work out that you've married the beautiful guy to the ugly guy. You'll just get it right. You'll just know it's right. And then you'll have the answer. So if you're pressed for time, you can answer these kind of questions in like 20 seconds just by finding the beautiful guy. All right, look at this. What is the beautiful guy marries the ugly guy?
Square root of n over n.
Yeah, so try square root of n over n, which is nothing other than 1 over the square root of n. Yeah? Because what do? We just dropped everything that wasn't the leading order term. So this 1 is not really important, so on the top we think of it like the square root of n. The 2 is not important, so square root of n over n, which is 1 over square root of n. That's our guess. Yeah? So try to marry them. So we take this guy, the ugly guy, we divide by the beautiful guy. That's the same as square root of n times plus n over 2 plus n. Let us let's factor out an n from the top. So the square root of n, then we're going to have the square root of n, the square root of 1 plus 1 over n, like this. And let's factor out an n from the bottom, 2 plus 1 over n. Yeah? Square root of n times square root of n is n, so this is n over n, so then we have this thing. And then we know the limit of the top is just going to be 1, right? The limit of the bottom would just be 2. Yeah? Because as n goes to infinity, this is going to 0, this is going to 0. So let's call this thing star. The limit as n goes to infinity of star is just equal to 1 over 2. Huh? So they're married. And what does the beautiful guy do? What about this thing?
They're both going to diverge.
Yeah, this thing diverges. And so the ugly guy also diverges. And that's it. Easy, no? Easy. All right. So the way to get good at this is to just practice finding the beautiful guy when you look at the ugly guy. And if you do whatever, 10, 15 examples of this, you will quickly find how to do that. Yeah? And when you're starting off, you're going to need to check carefully that you've done it right, that you've chosen the beautiful guy that marries the ugly guy. But you'll see that very quickly you will get it right all the time. You will pick up the real structure of this series, what it's actually doing, what the important essence of it is. And then for multiple choice, you can rip through these questions. You can just rip through them by looking at this and going, okay, basically this guy is like 1 over square root of n. And I know I have a theorem that says that that's true, that if I can marry this guy to 1 over square root of n, which I can, then whatever 1 over square root of n does, this guy does, and therefore I know this thing diverges. Yeah? Yeah? And even when you have questions where you have other series and you need to apply different techniques, you can still check it with this thing. Just find the beautiful guy that marries this guy, and then determine what the beautiful guy does, which is almost immediate because it's something very simple. This is a great tool. This is a great tool to get good at. All right, everybody happy? All right, super. Have a good day, and I will see you all on Monday.